maybe Miguel Angel, if you want, we can start and
okay.
And to introduce Jan.
7:05 or it's okay. Okay. So yes. Let me go back. So share the screen. Hello. So hello everyone. So well, welcome to this 7th MATHCHAT seminar. We have today Professor Jan Wehr, who has been kind enough to give us this seminar from the US, from the University of Arizona. So it's very early, well not so early, it's early now in Arizona. Professor Wehr is a well-known applied mathematician. He really comes from the mathematics background. Maybe he corrects me afterwards. He's originally from Poland, but he's been in the US for many years now. And well, he will talk us about some stochastic equations, some application of stochastic equations to very advanced problems with experiments. So I think it will be a very nice talk. So with this, it's my pleasure to leave you with Professor Wehr.
Okay, thank you very much. Let me just do the screen sharing thing as fast as I can. Yeah. Okay. There we go. Okay, so let's start. Thank you very much. It's very nice to be there, whatever that means. I am really grateful for the invitation, for an opportunity to speak. I'm not a sophisticated computer user, so I wrote parts of my talk in hand, and I'll be adding more things as we go. One question is, can you see me in addition to what I'm writing? It's probably more natural that way, but I think I have the video on, right? Okay. Very good. So, as Miguel Angel said, my background is mathematics, more applied recently than anything else. I work closely with physicists, and what I want to talk about today is a joint work with a physics group, and notably with Giovanni Volpe. Here is a list of my all collaborators. Giovanni is an experimental physicist at the moment at the University of Gothenburg. Mite Miyalkov was his student when the main experiment was conducted for the first time. Austin McDaniel was my student at that time, and he did most of the calculations. Maximilian Lehmann and Freddy Ogemark are students, were later students in Sweden, and they conducted further experiments. I may get to these more sophisticated experiments later on. Finally, Jeremy Birrell is an extremely talented young mathematician in the US, with whom we're working on further mathematical ramifications of the theory, and I would like to at least mention that work at some point during my talk. Now, the talk is going to be at the theoretical level about exploring a terrain. So what we're imagining, let me reduce this slightly to fit the screen. What we're imagining is we have an unknown terrain and we want to explore it, having at our disposal for the moment one mover, one robot, because in the experiment it was in fact a small robot. And I'll explain what essential features our exploration of a terrain is going to have, so that I can explain why I wrote the equations that I wrote as equations of motion. ultimately we'll be interested in a group or even a swarm of robots, and we will want to know how they interact with one another. But for now, and for the most part of the talk, we are going to focus in more detail on the motion of one such mover, such one explorer, and we are going to see what sort of consequences this has for group behavior, emergent group behavior. So, the terrain is inhomogeneous, and that translates into position-dependent speed of the movers. Depending on where they are, they move faster or slower. In order to explore the terrain effectively, efficiently, they have to change the direction. If you're moving in a straight line, you're not going to explore much. And they will adapt their speed to the conditions. They will adapt their speed to where they are, but they are going to first sense the environment, and sensing and then translating this into an altered speed is something that takes time. Hence, there's going to be a sensorial delay. Now, that, of course, is a fact of life. Everything is happening in real life with a little bit of delay. The main theme of this talk is that, very far from being an annoying feature, this delay can be used to our advantage, depending on what sort of behavior we want to engineer in the system. And finally, the motion is going to be fast. That means, mathematically, I will want to take a certain limit and show that in this limit, the equations simplify and yield a certain effective motion. Taking such limit, of course, is a mathematical procedure, and it can be only justified ultimately by an experiment. And in this case, it was, and I'll try to tell you a little more about how the experiment was conducted later on. So now, for the equations of motion, we are moving in the plane, in a region of the plane. So we have two coordinates, x and y. They depend on t. And the equations of motion are simply that the time derivative of x is the local speed times the cosine of the angle that decides what the direction is, and the same thing for y, except there is a sine rather than cosine. And now all the features that I mentioned come into play. So first of all, the speed is position dependent, but it depends here in the equations not, it's calculated not at the location where the mover is currently at time t, but at some earlier time. And also the angle that says in which direction we are moving, that angle is changing in time, and it's changing randomly. Now, the fast motion is enforced by the factor 1 over epsilon. Epsilon is going to be taken to 0. And you see the same 1 over epsilon in front of the equation describing the evolution of the angle. What you see here is random direction changes, because eta t denotes here Gaussian white noise, normalized to be unit Gaussian white noise, so that 1 over epsilon sets its effective scale. You see the parameter c here, and you see the delay, which is proportional to epsilon squared. This is because we want to obtain a meaningful limit as epsilon goes to 0. If epsilon scales as a larger, if the delay scales as a larger power of epsilon, we don't see any effects of the delay in the limit. If it scales as a smaller power of epsilon, the limit doesn't exist, or we don't know how to take it. So this is tuned in order to have meaningful, for the system to have a meaningful limit. And again, this is justified finally by the experiment. So these are the equations that I would like to work with, and I cannot, because they are way too difficult to study, especially if I don't take the limit of epsilon going to 0. But even with that, These are stochastic equations because of the randomness in the equation for the angle, and they are stochastic delay equations because of the presence of the sensorial delay. Way too difficult to study analytically, so I'm going to take some simplifications. And these simplifications are essentially first order approximation. We are going to expand the functions, the functions that enter the equations, which are v, x, and y. V is the speed, x and y are the coordinates, to first order, then rearrange the terms, and then do a further approximation by neglecting terms that are of higher order than epsilon. I'm not going to bore you with the details of this calculation, which is fully elementary, and every time I do it, I make a mistake, and I have to redo it. But last night, I recreated the whole calculation, and it's correct on paper, and this is what you see. So you see 1 over epsilon term, and I wrote everything in the notation using differentials rather than time derivatives, because I want to conform to the notation used in the theory of stochastic differential equations. In particular, I replaced the equation for the angle by putting the differential of the Wiener process here, and the relation to the white noise that you saw on the previous page is that this Wiener process is its time integral. That's, of course, a distributional quantity. We don't need to worry about this, but you can just think about the random walk, angular random walk, and this is how it was engineered in the experiment, because after all, there had to be a time lag between one time change and another. But in the mathematical model, that's what it is. And then you see various cosine and sine terms. The subscripts here denote the derivatives with respect to either x or y. And I skip the arguments of the functions v, vx, and vy, because they are now all locally evaluated at xt and yt. Once I've done this approximation that linearized v and x, that expanded them to first order, I no longer have a time delay in the equations that translated into a presence of additional terms in the equation. There's some algebra that goes into that, but there are no special tricks or further ideas necessary. You just rewrite the system like this. And I want you to notice that this is what's classically understood as a system of stochastic differential equations. There are 3 dynamical variables, x, y, and phi, and the system is propelled, driven by one noise source. That noise source is denoted by W here. It's the driving Wiener process. What I'd like to do is take epsilon to the limit, epsilon to 0, and what I'm asking is, do x and y converge in that limit? So in other words, I solve the system, or I consider its solution, because I cannot solve it explicitly, at a given value of epsilon. I look at the solution. The solution is, of course, a stochastic process, because I have a stochastic differential equation. And then I'm asking, do these processes converge as epsilon goes to 0? Well, certainly not the phi variable. Phi variable is going to diverge. It's a fast variable in the system, but I want to know whether x and y converge to processes, limiting processes, that will satisfy a certain limiting equation. That would be ideal. That's what I'm after. I would like to establish something like this, and I will. So that's the setup. That's what I'm trying to do. And in order to work on that, I'm going to introduce a little bit of knowledge from stochastic differential equation theory. It's a crash course in stochastic analysis, if you want. So a general system of stochastic differential equations looks exactly the way that our system looks. There's a number of dynamical variables here indexed by I, and they satisfy equations of the format dxi is equal to some drift term, and then a number of noise terms. There may be several noise sources. They are labeled by alpha here, and then they enter the equations with coefficients that I denote by sigma I alpha, the noise coefficient, sometimes called diffusion coefficients, which I think is a little confusing. So once again, the system I'm considering is of that form, but there's actually very few noise terms in it. There's only one, and in only one of the equations. The other two equations only contain the drift terms. And my apology, I forgot to write dt multiplying this whole expression and this whole expression as well. All of this should be taken in parentheses and multiplied by dt. I ran out of space and I forgot about that. So that's the object we are studying. How do you study objects like this? So a time-honored procedure of studying SDE theory is to pass to an associated partial differential equation which contains no randomness. You trade an ordinary differential equation with noise for a partial differential equation without noise. And every physicist knows this, of course, at the level of the so-called Fokker-Planck equation. What I'm writing here is a very close relative of the Fokker-Planck equation. It's the Kolmogorov backward equation, where Fokker-Planck is Kolmogorov forward equations. There are reasons why backward equations are easier to study. I do not want to go into that right now. If you like Fokker-Planck equation better, everything that I'm going to say could in fact be carried out at the level of the Fokker-Planck equation using it rather than the Kolmogorov backward equation. Only the calculations would get a little more complicated, but the idea is the same. So the Kolmogorov equation is generated from our stochastic system by writing a second order differential operator in the x variables with coefficients that are derived from the drift and noise coefficients of the original system. And then you write the diffusion equation with that operator on the right-hand side. So the equation is for the unknown function g of the variables t, which is time, and x, which is our space variable, so it has all the components xi that the original system has. And the equation reads dg by dt equals a certain differential expression of second order in the variables x. Now the coefficients of the first order terms are the drift coefficients of the original equation. The coefficients in the second order part come from the noise coefficients via essentially the multiplication of the matrix sigma by its transpose. And here is the explicit formula. And the important fact here is that not only can you derive the Kolmogorov equation from the SDE, but you can also reverse engineer, you can recover the SDE from the Kolmogorov equation. What this means is that our limiting procedure, what we are planning to do, taking the limit of epsilon going to 0, can be carried out at the level of the partial differential equation, where there is no randomness, after which, when we are done with taking the limit, we go back to the SDE language. And for many reasons, in this case, this is an important, this is a convenient way of doing things. And this is what we did. In fact, we want to improve on that, and I'll say a few words about that later. But for now, this is where the matter stands. So that's the plan. We want to take this limit, the limit as epsilon goes to 0 of this system, but we want to use the Kolmogorov equation as a tool. So pictorially on a diagram, this plan looks as follows. I have a stochastic differential system indexed by epsilon. I want to take this epsilon to 0. Rather than doing this directly, I first pass to the Kolmogorov equation, which again has this label epsilon because I haven't taken any limits yet. Then I take the limit with the Kolmogorov equation and I obtain Kolmogorov 0. The limit has already been taken. And from it, I recover the stochastic differential system at 0. So the arrow that I really wanted to carry out, that limit, is done in an indirect way passing through the associated PDE. And of course, the devil is in the details of this arrow. And this is what you do there, and what I'm not going to bother you with today is called the multi-scale expansion, and it goes by several different names. You may recognize some of them: homogenization, singular perturbation theory, or more physically, adiabatic elimination. Let me comment on that. We have said that in our original system, we had 3 variables, x, y, and phi was diverging. Phi was the fast variable. This is the variable that we are eliminating. In the limiting equations, we are only going to have x and y, but no phi. And you can think about phi as a variable that's changing so fast that the effective motion of x and of x and y got averaged over these very fast erratic oscillations or fluctuations of the phi variable, and x and y move much slower, hence the word adiabatic, and this is what the main idea of adiabatic elimination is about. So I'm skipping that part for the lack of time, and also because treating people to these calculations is not really fun, primarily not fun for the audience, but the reassuring fact is the calculation is almost algorithmic. You know what you need to do. You need to carry this out without making any mistakes, and these are calculus calculations, but there's plenty of them, and you have to carry them out carefully. Here is the result. What we called Kolmogorov 0 is now a partial differential equation, and as promised, it's a partial differential equation in 2 variables only, the variables being x and y. Phi has disappeared or got averaged over. And it comes out like this: dg by dt, g is a function of t, x, and y, is 1 minus a half of c. C was this parameter in the original equations that was dictating the exact size of the time delay, the sensorial delay. It enters here in this form. And then you have v times the x derivative of v multiplying g, analogous term in y, and then v squared times the Laplacian of g. And now you carry out that part. You recover from the Kolmogorov equation the corresponding system of stochastic equations. Now, if you just look at the correspondence between an SDE and the associated PDE, you see that the second order terms in the PDE come from the noise coefficients in the SDE. If you have 2 of them, as you do in a Laplacian, then this can only come from a presence of 2 noise sources in the stochastic equations. You can figure this out if you look at this correspondence very easily. So when I am reverse engineering my system of SDEs, I'm forced to employ 2 independent noise sources, one in one equation, the other one in the other equation. That corresponds in the language that I used earlier to 2 terms in the sum in the noise term, that is to say 2 different values of alpha. These are independent Wiener processes now. And this constitutes a little bit of a puzzle, because in the initial equations, I only had 1 noise source, this eta or w, if you prefer, which was the time integral of this eta, as I wrote earlier. Now I did this magic procedure of adiabatic elimination. I somehow passed through a PDE level where there was no noise visible, I went back to stochastic language, and lo and behold, I have 2 noise sources where initially I had 1. This is something we did not understand initially. And I'll tell you what the reason for this is first. Let me first say, why there is no obvious contradiction with anything. And this has to do with the question that I asked earlier: in what sense am I taking this limit? In what sense do the solutions of my simplified system that I wrote earlier, this one here, in what sense do these processes converge? So this is technically, for the mathematicians in the know of the theory, weak convergence or convergence in low. Because I'm passing through the Kolmogorov generators of the process, I actually am only studying weak convergence of processes. There's no contradiction in saying that the limiting process is described by a set of equations driven by 2 independent noise sources. This can very well be because we are not relating them at this stage in any way to the original noise source W. All we are talking about is how the realizations, the paths of the processes are distributed. And that's perfectly consistent. There's no contradiction. One would still like to understand how these 2 noise sources come about, and I'll address that point in just a moment. But that's a mathematical point, and I want to talk more about the physics because the project was really experiment motivated and experiment oriented. One thing that you can see easily in the experiment is that there is some noise that I think someone has not muted himself. I can see some children, which doesn't bother me too much, but I don't want to know anyone's family secrets. Thank you. So one thing that you can see easily in the experiment is the stationary density. And you can also calculate it, and in fact, from the conjugate equation to the Kolmogorov equation, from the stationary Fokker-Planck equation. I'll skip the calculation, but you can do this explicitly and find the density, the probability density, the density of the probability distribution that's stationary under the evolution of the limiting system, the system that I got, describing the evolution for x and y. And the formula for this density is that it's a constant, normalizing constant, times the function v. Remember, v is a function of x and y. So this is a non-trivial expression, depends on the position in the planar region where the explorer is moving, in the power negative of 1 plus c over 2. And the first time you think about this, you look at this, you say, okay, what this is saying is that the probability is smaller, the probability of finding the particle or the robot is smaller, where the speed is larger. There's nothing exotic about that, because if it's moving faster, it's going to spend less time there. It's going to linger on for a longer period of time, where it's moving slower. Not a big surprise. It's actually interesting that it depends on the value, the precise value of the delay constant c in this specific way. It's nice that it can be calculated this way, but there is really no big surprise in that, until you realize that, in fact, the way we have done things, c may also be negative. And at first, when you hear that, you say, no, this is nonsense. My c is the time delay. The explorer looks at what the terrain is like and adjusts the speed. That takes time, of course, but it wouldn't make any sense to make c negative, because that would mean that the explorer knows where it's going to be in the future, which of course it doesn't. However, we have linearized these equations, simplifying them, and we wrote them in this form. And in this form, they are perfectly meaningful for a value of c that would be positive as well as negative. And in fact, in the experiment where we had to program the robots to follow certain equations, the program asked them to follow these equations and not the original equations with a delay. And there are examples of biological systems which do similar things. Bacteria, for example, are known to practically take a gradient and predict where the concentration of a certain chemical is going to be larger. I do not want to go into details, but this actually should be mentioned because one of our motivations in this project was to work on chemotaxis. This is not a model of chemotaxis because model of chemotaxis requires time dependence on the v, on the speed function, where actually we have a project on that going on as well. But what I'm trying to say is there are natural situations, in particular man-made situations, in which it makes perfect sense to think about the constant c as negative. And then things may change when c goes through a critical value of -2. If c is less than -2, if it's so negative that its absolute value exceeds 2, then you have a counterintuitive effect of the particle spending more time where the speed is large. Somehow, it manages to do it, even though it, of course, zooms very fast through the regions where the speed is large, but nevertheless, it ends up spending more time there on average, as measured, as shown by this formula for the invariant density, for the stationary density, which is confirmed in the experiment. Now, how do we engineer this in the experiment? What we actually do is we have a robot that's light sensitive. And the way it reacts to the amount of light, to the intensity of light that it sees, is by moving slower where there is more light. So it's not propelled by light, it's kind of stopped, impeded by the light intensity, and moves faster where where it's darker, in a darker region. And so the qualitative analysis on the previous page can be summarized by saying that when C is positive, or at least not too negative, the robot prefers to be closer to the light source. In other words, in a slower region, because it's moving there slower, and for this reason, it will stay for a longer period of time there. That's this normal, more intuitive behavior. But below the critical value of -2, the robot prefers to be further away from the light source. And this leads to the following idea. Instead of a single robot exploring a terrain, let's actually think about a group of robots, a swarm of robots, and each one of them is going to emit its light. So the situation is as follows. You have a number of particles in the plane. They're all moving and doing what we described earlier, moving in directions that change randomly. And at each moment, every one of these robots is emitting light. And so if I am this robot, I'm taking the sum of the light intensities from all the other robots, but not my own. I don't see my own light. And based on that, I decide whether there's a lot of light or whether I'm in the dark. And I adapt my speed to that. If I see more light, I move slower. If I see less, I move faster. This is not exactly the original problem that we started from, because in the original problem, we had a fixed function v. And now the function v is changing because it depends on where the other robots are. Nevertheless, the calculation that we did for a single robot can serve as a motivation, as a sort of a mean field approximation to what a single robot is going to see on average. And now we go back to the previous page and we ask, so where will the robot want to be? We learned that it wants to move slower where there is more light. And what that means is that it prefers to be closer to the light source, but the light source are other robots. And so if C is greater than -2, then each robot will prefer to be close to other robots because there is more light there. And that will translate into aggregation. This robot will say, I want to move closer to where the other guys are because I want more light. I'm moving slower there, I'll spend more time there. In the regime where C is less than -2, you'll see the opposite effect. The robot will say, no, I actually want to be further away from the light source. The light source are the other guys. I want to stay away from them. And this translates into deaggregation. Now imagine a situation in which you can, in fact, control this parameter from the outside. You have a swarm of robots. They are all characterized by this parameter C, and you can change it at will. So you can send them on a mission, and they're going to aggregate as long as C is greater than -2. Then you'll turn the knob, and they will start deaggregating, and you can flip between the two behaviors. Of course, there's some time that it will take for them to aggregate or deaggregate. We actually carried out the experiments with several, at the moment, up to 5 robots, and have seen very clearly these aggregation, deaggregation phenomena, depending on the value of the delay. We carried out also extensive numerical simulations with, I can't remember right now how many particles, I think several hundred. And you see that also very clearly. In the abstract of the talk, I gave a link to American Physical page with a description of that experiment and the whole work, which was actually not written by us. It was done by a science writer for the APS, but done very well in non-technical terms. Also, what you can see on that page is a little movie showing aggregation, deaggregation phenomena that we're talking about. Once you realize that this is a possibility, you see that it's natural to work on such a system where our motivations were things like, for example, sending robots on search and rescue missions where you can first spread them over an area and then make them aggregate, collect them at one place when you no longer need them or want to collect them back, carry them away. Since the similar model, more complicated, can be considered in 3 dimensions, you can think about situations with a spatial structure, such as swarms of perhaps flying agents, or such as microrobots inside a human body sent on a medical mission. This was in fact the original thing that we thought of, because in biomedical engineering, there are projects of using swarms of really tiny microrobots in order to cure certain tumors, but the problem, of course, is you cannot send such a swarm through human tissue through one channel, because then you're going to destroy the tissue. So the idea of spreading them and then collecting them, deaggregating first and aggregating next, becomes very natural. I should mention that the 3-dimensional calculation was carried out almost entirely by Austin McDaniel, and it becomes way more complicated, but it can be done, and the qualitative behavior is similar. Actually, C becomes -3, the value, the critical value of the coefficient C becomes 3, but you have 3 components, X, Y, Z, and calculations get way more involved. Finally, I would like to go back to this mathematical puzzle and explain why we get two noise sources in the limit, and also explain why the equations look the way they do. The way we obtain them, well, first of all, I didn't show you the calculations, but even if I did, you obtain these equations from essentially machinery. That procedure of multi-scale expansion is not really transparent. You go through certain motions, you write lots of formulae, and out comes this, and from this comes that. And then you're looking at these equations and you're saying, oh, okay, this is what I got. But the question is, can one actually recognize in these equations the equations before we took the limit? Can one, looking at the original form of the equations here, predict that the limiting equations are going to look like this? In particular, can one find the source of these two noise terms in the original equations? And the answer is yes. This is how it's happening. And that's the content of the ongoing work with Jeremy Birrell. And we think we have it, but we haven't written it down yet. It's our next paper. The 1 over epsilon terms are giving us the noise terms according to the following somewhat perhaps surprising fact. If you have a single Wiener process, and let me remind you that phi is a rescaled Wiener process, then you can obtain two independent Wiener processes from it in the following simple way. Just by taking the cosine and the sine, you kind of decouple the random degrees of freedom, and you get two independent noise sources from one. I could give this talk a title if I was giving it a more mathematical bent. How do you obtain two independent Wiener processes from one? It's not such an obvious question. If you ask this question to a probabilist, they will usually tell you, I don't know, it's probably possible, but I have no idea how. This is how, and I learned this from a physicist, Denis Bernard, actually an excellent physicist at the École Normale in Paris, who encountered that phenomenon in a work on quantum optics. And once you notice this, the rest is easy. You look at the cosine squared and the sine squared terms. They just average to a half. You look at the cosine times sine, it averages to 0. So this tells you what will all these 6 terms turn into. And then there is one more ingredient. If you look at the limiting equations, where do I have the limiting equations? Right here. We have accounted for the presence of the noise terms. We have accounted for the presence of 1/2 terms. That's where they're coming from. And then there's also VVX and VVY coming with the coefficient 1. What this is, and you see this highlighted here, is the Stratonovich terms, Stratonovich correction. So again, for those in the know of some stochastic analysis, what happens there is sometimes in addition to the noise term, you have to include what you obtain by taking the coefficient of the noise term and multiplying it by its derivative times 1/2. This is how you get VVX dt here, and this is how you get VVY dt. And that's related to the fact that the terms that give rise to the noise eventually are not pure noise, they are regularized noise. They don't have the Wiener process in them. And for that reason, what we are doing is we are approximating the noise in the limiting equations by a more regular process. That's usually a signature of the presence of a Stratonovich correction. And this is really the main thrust of the work that we're doing with Jeremy right now. So to summarize, we have carried out a really very applied problem, the central ingredient of which was the experiment, which was first carried out by Giovanni and Mite. Maximilian and Freddy added also a position-dependent speed of the random time changes, random direction changes. I do not have the time to talk about that, but it actually leads to interesting further effects, in particular to a presence of a macroscopic drift in the system. That's a newer work which is already published, I think in Physical Review E. Finally, there is an interesting mathematics extension of the project, which studies the reason for the form of the equations and justifies the presence of what is a Stratonovich correction mathematically, but in a novel situation which was not known so far. So with that, I would like to end. Thank you very much for your attention, and I hope there will be some questions, but right away I'm going to say you know how to reach me, so if any questions occur to you later on, please don't hesitate to write to me. I'll be very happy to discuss things with you. Thank you again.
Thank you very much.
Thanks very much, Dan. So let's is there any question, comment? I have a question.
Thanks, Janek. So now we go for questions.
I can't hear you very well.
Okay, I have a question. I'm Alberto.
Yes.
So in this part of exploration, there were some works about sharks in the sea that they do levy flights for trying to look for prey. So but with this approach,
who wants to?
Yeah. So this is a different model.
Yes, it's a different model, but the thing is that this model seems to me that you are more in a vicinity or in a neighborhood, and it's more like for the phase that you are closer to, and you want to explore a limited space, probably the rover in Mars. But this later combined with other approaches if you want to explore a wider area, or?
It could potentially. We didn't do this. What it would involve would be a different noise source, different form of the random term in the equations. Now, actually, Giovanni was involved in a somewhat related work where he was using Levy flight approach in a disordered medium. He wrote a paper, a theory paper about that with Giorgio Volpe, actually his brother, which I think was published in the bulletin of the American Academy of Sciences. But we did not try the homogenization approach for this, but it's a very interesting question, and actually I'd like to go back to it at some point.
I guess that since you were thinking also about somehow the consensus or about the approaching one robot to the other, so it was more a local phenomena than something that you want to spread for a big area, or not?
It's true, but I think you can ask the question whether establishing the territories for predators might be related to that, and perhaps a model using Levy flights would be appropriate for that. This is just a thought. I haven't thought about it very deeply, but now that you mentioned this, deaggregation is something that does occur naturally in populations of predating animals, and so perhaps, you know, as I'm looking outside of the window, I'm looking at the hummingbirds here. They're a very good example of that kind of a behavior. Yeah.
Okay, thank you very much.
Thank you.
Hi.
Hello.
This is Juan Carlos. Thank you very much for your talk. My question is more technical. If I understood correctly your approach, you transfer the system of stochastic differential equations into the Kolmogorov partial differential equation, which is deterministic. Okay.
Yes.
So any more questions?
And afterwards, you propose a pattern, a solution of the stationary solution for the PDF. And so my question is, why are you interested just in the stationary solution instead of the transition solution?
No, I'm.
Solving
It's not that I'm only interested in the stationary solution. The stationary approach comes in only when let's see, where is the page? Where I was looking at the stationary density. But in fact, the result of the calculation gives us the full dynamics in the limit. So when you look at the what I label as SDE0, this is dynamics of the system, and it actually has the transient as well as the stationary regime encoded in it. You derive the expression for the stationary density from these equations or from the associated Kolmogorov, but they have way more information than just the stationary behavior. They are fully dynamical equations.
So in that case, are you able to obtain the transition PDF? I mean, for any time?
Not in a closed form, or at least we didn't try it. But numerically, of course you could, yes. But actually, so we haven't tried it. But I think this is a relatively simple system. And since you can solve explicitly the stationary equation, it's not completely impossible that you could get the transition function in an explicit form as well. I do not know. We haven't done this because in the experiment, what was mostly measured was the stationary distribution, and so mathematically we were thinking more about that. But it's a very good and certainly legitimate question. I would have to think a little more to give you a qualified answer.
Okay, thank you very much.
No, thank you.
Okay, any more questions?
Hi, I think I might have a question. I'm a mathematical physicist by trade, and seeing your results here, I can't help thinking of the quantum mechanical wave equation. So the Kolmogorov equation is closely related to the Schrödinger equation. What is the relation between the density and that function g that you're showing here? Because my first thought, my first impulse would be the density is g squared, or squared modulus of that. Is that true?
No, this is not a quantum equation. Nothing is complex here. And
no way too far around, but I'm just reasoning on a purely formal level. I see a Laplacian and I see a term containing think of as being a potential, and you also have a parameter that you can fine tune, which is c, and that c controls the behavior between aggregation and deaggregation. So you can think of that t as fine tuning between, say, a bound state and a scattering state, for example, right? So that's a kind of analogy I'm trying to draw in my mind. But maybe it doesn't go beyond a mere analogy.
No, I think that the more complete analogy is between heat equation and this equation, but not Schrödinger. So, of course, formally Schrödinger equation and heat equation are alike because derivatives of similar orders occur there, but the presence of the imaginary unit turns diffusion into wave phenomena. You don't have waves here in this equation, only diffusion. So it's as far or as close, depending on how you look at things. Of course, there is the general analogy, but it does not go further than the analogy between heat equation and Schrödinger equation.
Okay, thank you.
You're welcome.
All questions? Then other question? If not, I do have a question, Janek. If you can go to the initial equations, so it's only clarifying
Sure.
the system and the role of delay. So, okay. So we have X and Y, which are the variables associated to the position of one of the robots or many robots, and the noise affects only to the angle. So in the experiment is rotating a little bit randomly the angle, correct?
Mm-hmm, mm-hmm.
And then there is a delay on the response. And then we went very quickly about the analogy with bacteria. When you have a delay that sometimes can be negative or positive, so that means they are predicting the future. And I know this delay is crucial. Well, you already saw that this delay is crucial. So can you simply explain a little bit about how bacteria do this? Well, there is this homogeneous B, which is also important.
So,
at the end, like,
okay.
But this, yes.
So I'm certainly no expert on bacteria, but the way I understand this is the bacteria is taking two measurements, and it manages to calculate the derivative by comparing the results, which is amazing for an organism this simple. But I'm told that this is actually underlying some chemotactic mechanisms. I haven't read about this extensively, so I'd rather not expand on that because I don't want to say something incorrect. But the people who know more about this that I listen to tell me that you can try to base a model for chemotaxis, simple model for chemotaxis, on that. And as a mathematician, all that I can do is I can ask, is this enough to, for example, model a motion of a bacteria against the chemotactic wave? Because what's happening in the chemotaxis case is you actually have a situation where a source is emitting a concentration wave of a chemical, and so what you obtain is a function v, the speed function, that would, in this case, in the simpler, in the simplest case, depend only on one of these variables in the following way. Let's say omega times T. That's when you believe that a bacteria can carry out this measurement and interpret its result by adjusting its speed. Now the question is, can you then add a delay to the motion so that you have this chemotactic center that emits this wave and a little creature that's moving against that towards the center? And what we see from calculations is, yes, that you can do that. You can. So that would be another argument why delay can be used in a constructive way in order to engineer desired behavior. Now you may ask, how is the bacteria going to adjust its delay in order to optimize its movement? And the answer is, I don't know about this case, but I've been to a talk where the speaker was arguing that delay in some biochemical reactions is in fact evolving preferentially towards the value that makes certain things possible. It's not becoming faster. The reactions don't take smallest possible time in order to become more efficient, but they actually are delayed in order to make certain things, certain other things optimal. So it's not impossible that in bacteria, the delay with which they sense the environment would also evolve in an adaptive way, but I don't know this for a fact. I'm looking at this as a mathematical model at the moment, and it would have to be established by an experiment eventually. I think something got muted here, no?
No, it's okay. It's okay.
It's okay.
Okay,
Yes.
okay, fine.
It's okay.
Perfect. Okay, so that's all I can say about that. Again, I wish I knew more about bacteria and how they do this, but at the moment, that's all I can say.
So if there are no more questions, Miguel Ángel?
Well, this is Juan Carlos again.
Ah.
Can I raise another question?
Sure.
Yes.
Yes. Okay. So I'm wondering how about considering another kind of noises rather than using the Wiener process and the white noise process, using more regular processes about the movement regarding the angle. Is this possible? Is this more natural or not?
Well, natural or not depends on the situation one wants to study. In the experiment that we worked on, actually full independence was natural. But of course, it's a natural question for other applications to make the noise more regular. And then, yes, I think it would be possible to do. Essentially, in similar situations, what one does is the following. The natural first candidate for a more regular colored noise is the Ornstein-Uhlenbeck noise, for which you write the equation. So this phi then would satisfy a stochastic differential equation, which would be more complicated. There wouldn't just be a Wiener process on the right-hand side, but there would be a time scale associated with the correlations of the noise phi, which now has correlations because it's colored, and the equation would look like this. If you denote this time scale by tau, you would write here dt, and then 1 over tau times dwt, where this is the driving independent noise source, but you don't put it as such in the row form in the equations, but you filter it through this equation so that you obtain phi that's correlated. And then the stationary solution for this SDE is Gaussian, obviously, because the coefficients are constant, with the expected value phi s phi t given by the formula exponential of negative s minus t divided by the tau scale, time scale tau, and then normalized properly. So let's see, like this. Okay, and what one would have to do would be to add this equation to the original set of equations that we are studying. And then, in order to take the limit by a multi-scale expansion or by any other technique that one uses, one would also have to scale the time scale of the correlations in an appropriate way with the parameter epsilon that we are taking to 0. And offhand, I cannot tell how it would scale, but my first guess is tau would have to scale linearly with epsilon in order to obtain a meaningful limit. And I definitely think it would be possible to carry out.
Okay, thank you very much, John.
Yeah, I think it could be done if you see a reason why this should be done. It would be a complicated calculation, but doable. I encourage you to write me an email and say why one would want to do that, and I would be happy to see if I'm right, guessing that that it could be done. Yeah.
Okay, thank you again.
Mm-hmm.
So sorry, I had some problems with the connection. So any more questions?
Well, if I can do another question, I have the curiosity to know how do you calculate in practice the value of parameter C? I mean, in practice, the delay must be set from measurement, from data, probably according to the robot's movement. So, with kind of thing to fix the value of the delay C.
No, actually, in this experiment, we could tune the parameter C. We could program it into the robot's motion.
Okay.
Because these are programmable robots. And in any man-made system, this is what you want to do. It becomes one of the control parameters.
Okay.
In possible applications of similar equations, not exactly the system, but similar equations to describe biological systems, your question becomes very relevant. And the answer is, I do not know. As you already have figured out, I didn't really do the experiment. So it was done by my collaborators, and I do not know. It would have to be done, of course, by carefully analyzing the data. But in the experiment that was carried out with the robots, these robots are very sophisticated creatures, and you can program all sorts of things into them, in particular the time delay.
Okay, so you are not dealing with an inverse problem because you have the data from programming the robots. Okay.
Yes.
Thank you very much again.
Yeah.
So is there more questions? So one further curiosity, Janek. So at last, bacteria are also active matter. No? So all this can also be seen from the point of view of active matter.
Yes. Yeah, but if you want to include the activity of the matter in this model, then you would have to change the noise in a serious way, more serious than that. Okay? Again, a very good question. If you have not a single bacteria moving through a chemically active but biologically passive environment, but if you have a swarm of bacteria moving together, then you would have to add, you would have to really think carefully about how to model the noise. And that's a very interesting question, but we didn't get this far yet. But absolutely, that's the question that one should ask if one wants to study things that are biologically relevant. You see, in the situation where you have the robot swarms, the robots influence each other motion, the motion of each other through the velocity function, but not through the noise. Okay? In your question, you actually get one level up because you're asking, what about the noise? How is this dependent on the configuration of the robots? That's a more complicated story. Now, to some extent, we touch upon this in the model in which, let me actually say how you can modify the equation for the random time changes. Instead of writing simply what we wrote, dφt equals rescaled Wiener process, what you can write is, let's see, I'm trying to remember whether we wrote this in the numerator and in the denominator, and I can't remember, but I think whatever, it doesn't really matter. Where you write function sigma here, which depends on xt and yt and dwt. Okay, and you can have a delay here too. Right? But the idea is that the speed with which, the frequency with which you perform the random direction changes depends on the position as well. So what you can imagine is a situation where the amount of light from other robots influences that too. And in fact, such an experiment was carried out by Giovanni's students in Sweden, by Freddie and Max. I'm not sure this addresses the full extent of your question. I think there is more to it. I think you could imagine a different kind of noise, and I would have to think a little more about that. But I think if you really fully want to account for activity of the matter, of the surrounding matter, you have to go beyond even this model. You have to do something more sophisticated.
So I think there are more questions, or if not, we conclude here. Anyone else volunteers? If not, we cannot clap, Janek, but we thank you deeply for this talk.
Thank you. Thank you very much for the invitation. It was very nice.
Thank you, Janek.
A lot of fun. Thank you. Good to see you.
Thank you, all of you, for coming. So, well, now we leave the meeting, and have a nice weekend, all of you.
Okay. Have a great weekend too, and I'll send you the file with the recording.
Thanks, Janek.
Thank you.
Thank you.
Thank you very much.